In section 3.4, we'll be looking for the zeros of polynomials. We'll apply the rational zero theorem, use the fundamental theorem of algebra, and apply Descartes' rule of signs. Let's start with the zeros of a polynomial. First, the zeros of a polynomial are the solutions to the equation f of x is equal to 0. This is why they're called zeros, because we set the polynomial equal to 0 and then we solve for x. Now, one thing to note is that the real zeros of this equation correspond to the x-intercepts on the graph of y equals f of x. And we've seen this in the past. And finally, zeros are also called roots. So you may hear me say root instead of zero. Those are the same thing. Our first tool when finding the zeros of a polynomial is the rational zero theorem, also called the rational root theorem. And it says, if f of x is equal to this polynomial with integer coefficients, and the lead coefficient a sub n is not equal to 0, and if p divided by q, reduced to lowest terms, is a rational zero of f, then the p must be a factor of the constant term a sub 0, and the q must be a factor of the lead coefficient a sub n. Now we sort of use this backwards to produce the list of all possible rational zeros that could be zeros of the polynomial, and then sort of check them against those. I'll remind you that rational means integer divided by integer. So here when we're looking at p divided by q, this is an integer divided by another integer. Let's use the rational zero theorem in example 1. List all possible rational zeros of f of x is equal to 5x cubed minus 6x squared minus 9x plus 2. Then find the zeros and write f in factored form. So we're going to list the possible rational zeros, and I just call that the PRZ. Now from the rational zero theorem above, these rational zeros are in the form of p over q, and the p must be a factor of the constant term. The constant term is 2, so I'm just going to list all of the factors of 2, and that's just 1 and 2 because 2 is prime. And then the q must be a factor of the leading coefficient. And the leading coefficient here is 5. 5 is also prime, so its only factors are 1 and 5. But you would list out all of the factors, however many there are. And what we do next is we combine these two parts here, the p and the q, to form the PRZ. And we form it in this form with p divided by q. And we just take all possible combinations. So my first combination is 1 divided by 1 is 1. And then using the p that could be 2, divide that by the q equal to 1. 2 divided by 1 is 2. Next, we'll do 1 divided by 5, 1/5. And then 2 divided by 5. So I've created every possible combination of division with p divided by q. And the list is 1, 2, 1/5, and 2/5. Now also, we can use plus or minus for any of these numbers. It's sort of a common practice to just put a big plus or minus on the outside after you put the numbers in parentheses, and that suggests that every number in the list is plus or minus. You may have to put plus or minus on each number in your homework. And what this says right now at this moment is that if f has a rational 0, then it has to be one of these 8. It looks like there are 4 of them, but the plus or minus makes them 8. And so what we're going to do is we're going to find the rational zeros by testing these numbers and see what comes out. Now, what it doesn't help us with are the irrational zeros, like the square root of 2, square root of 3, and things like that. But finding the rationals is a good place to start. So what we do is we just test it, and I'm going to start with number 1. And we're going to do synthetic division on the polynomial. So it's 5, negative 6, negative 9, and positive 2. And if 1 is a rational 0 of f, then we should be able to do the synthetic division and get a remainder of 0. So let's do the synthetic division. Bring down the 5. 1 times 5 is 5. Negative 6 plus 5 is negative 1. Negative 1 times 1 is negative 1. Negative 9 minus 1 is negative 10. 1 times negative 10 is negative 10. We have a remainder of 8. So therefore, 1 is not a rational 0 of this polynomial. Let's try negative 1. And you just try these numbers however you'd like. No rhyme or reason to this yet. And we'll do the synthetic division. Bring down the 5. 5 times negative 1 is negative 5. Negative 6 minus 5 is negative 11. Negative 11 times negative 1 is positive 11. 11 minus 9 is 2. 2 times negative 1 is negative 2. And 2 minus 2 gives me a remainder of 0, and that one works. So, negative 1 is a rational 0 of the original polynomial. Now, once you have 1 0, your next task is to turn to the quotient and reform a polynomial based on this quotient. So this polynomial here is going to be 5x squared minus 11x plus 2. And I can tell that it's going to be quadratic because we have 3 terms. We would have the constant term, the x term, and the x squared term. With practice, you'll be able to just write that out straightforward like I did. We still have to find the other zeros, but now that we have a quadratic, we have other tools at our disposal. We can use the quadratic formula, we could complete the square, or we could factor. This one factors as 5x and x, a 2 here and a 1 here, with minus and minus. You can double check that that is the factorization. And these factors give me the zeros of x equals 1/2 and x equals 2. Combined with the negative 1 from the left side here, here are all 3 of our zeros. I can even use the factored form of the quadratic along with the 0 that we found on the left to produce the factored form of the entire polynomial. It's 5x minus 1 times x minus 2, and then since negative 1 is a 0, we know that its factor must have been x plus 1, because the factors are in the form of x minus c, where c is the root, or the 0, and we would have x minus negative 1, which gives me x plus 1. Let's look at example 2. Example 2. List all possible rational zeros of f of x equals x to the 4th minus 3x cubed minus 13x squared plus 51x minus 36. Find all zeros with multiplicity and write f in factored form. So we'll start by finding the possible rational roots again. So we'll have p, And the p, I can write out what the p is equal to, or at least the base number. The p is 36, and so that factors as 1, 2, 3, 4, 6, 9, 12, 18, and 36. The q is the lead coefficient, but since it's just x to the fourth in front there, that's a 1. So the only number that we get from q is 1. And that means the PRZ is equal to plus or minus, and then we just get the list from P again. So 1, 2, 3, 4, 6, 9, 12, 18, and 36. And of course that's because the only number that we could divide by is 1. So next, we just pick a number and divide out the polynomial to see if it is going to be a root. So let me write out the polynomial with just its coefficients here. So it's going to be 1, -3, -13, 51, and -36. And to do the synthetic division, I'll start with 1. Bring down the 1. 1 times 1 is 1. -3 plus 1 is -2. -2 times 1 is -2. -2 and -13 is -15. -15 times 1 is -15. 51 minus 15 is 36. And 36 times 1 is positive 36. Subtract 36 and you get a remainder of 0. Therefore, 1 is a 0. We have found one of the zeros. Now, we started with a degree 4 polynomial. So that means the quotient only results in a cubic polynomial. We don't have the cubic formula or anything like this. So what we do is we stick with this quotient as the new dividend, and then we try numbers again from the PRZ. Now remember that polynomials could have zeros with multiplicity. It could be 2, 3, or 4, or it could just be 1. Because 1 was a 0, it doesn't mean that it can't be a 0 again. So what I'm going to do is I'm going to pick up where we left off with this quotient that's now the dividend, and we're going to try 1 again. It may be a 0 with multiplicity 2 or more. So let's go on with this one. Bring down the 1. 1 times 1 is 1. -2 plus 1 is -1. 1 times -1 is -1. -15 minus 1 is -16, and 1 times -16 is -16. That leaves me with a remainder of 0, and so we did not get an extra multiplicity here. We still have the original 1 that worked up at the top, but that's it. 1 is not going to be another root. It's not going to have more multiplicity. So let's move on to another number. I'm going to move on to 3. I've got a good hunch about this one. And we're still working with the quotient that we ended up with from when we did find the root. This is sort of like peeling an onion. We peeled off one layer by finding this first root. Now I have to work with what's left over, which was this quotient. Bring down the 1. 3 times 1 is 3. 3 minus 2 is 1. 1 times 3 is 3. 3 minus 15 is -12. -12 times 3 is -36. And add that to 36. And yes, we get another root because we have a remainder of 0. Check. So now we have 2 of our zeros. We now have the quotient that's going to be 1x squared plus 1x minus 12. That is quadratic, and I can factor after I set it equal to 0. And this is going to factor as x and x, 4 and 3. I need positive x in the middle here, so I need a plus 4 and a minus 3. And then I can set these factors equal to 0 to give me x equals -4 and x equals positive 3. We can now write out the zeros with their multiplicity. So we have x is equal to -4 with multiplicity 1. We usually don't write the multiplicity if it's equal to 1. We can start doing that now. X is equal to 1 from the left side of the page. Multiplicity 1. And then here we have x is equal to 3 with multiplicity equal to 2. That's because we got one of the 3's from this bottom part and the other 3 from doing the synthetic division up top. Those are different 3's, so the multiplicity is 2. Finally, we can take this information and write out the factored form of the original polynomial. It's going to be x plus 4 times x minus 1 times x minus 3 squared, where the exponents come from the multiplicities. And remember that all factors are in the form of x minus c, so we essentially change the sign of the zeros. Next, let's look at the fundamental theorem of algebra. The fundamental theorem of algebra says the following. If f of x is a polynomial of degree n that is greater than or equal to 1 with complex coefficients, then f of x has at least one complex 0. And essentially that means that every polynomial of degree 1 or more has at least one 0. So that means we can always solve a polynomial with degree greater than or equal to 1. Continuing on, one of the results of the fundamental theorem is the linear factorization theorem. Basically it says if you have a polynomial with degree greater than or equal to 1, then it can be factored into linear factors. And those are factors in the form of x minus a number or x plus a number. The trick here, though, is that the numbers that it comes up with as the factors could be complex numbers instead of just purely real numbers. Now, a lot of times in the problems we'll work with, they're purely real, but they sometimes could be complex with imaginary parts. Putting these together, we get this little fact: the number of zeros of a polynomial. If f of x is a polynomial of degree n greater than or equal to 1 with complex coefficients, then f of x has exactly n complex zeros, provided that each zero is counted with its multiplicity. So essentially you're adding up the multiplicities to come up with the degree, because the degree is n, and they're going to be n zeros if you count them by their multiplicity. So this is a way to check to see if you have all of the zeros accounted for. If you have a degree 5 polynomial, you should expect 5 zeros if you're counting them by their multiplicities. Finally, the conjugate zeros theorem, or the also known as conjugate pairs theorem. If f of x is a polynomial with real coefficients, that's essential of this one, real, and if a plus bi, with the b not equal to 0, is a 0 of f of x, so if it is a root, then its conjugate, which is a minus bi, is also going to be a 0 of f of x. So if you have a polynomial that has real coefficients, and you have this complex number as a 0, then its conjugate is also going to be a 0. Let's see how to use that in example 3. Given that 2 minus 3i is a 0 of f of x equal to x squared minus 4x plus 13, what is the other 0? And then write f in a factored form. So first off, notice that the f of x has real coefficients. And since it does, we can use the conjugate zeros theorem, because we know that 2 minus 3i is a 0. That means another 0 is 2 plus 3i. That is the conjugate of 2 minus 3i. So this is by the conjugate zero theorem. Now, could it be that there are other zeros? And the answer is no. There are only two zeros because the degree of f is equal to 2, as seen right here. So since the degree of f is 2, there are only two zeros. We have found them. They are 2 minus 3i and 2 plus 3i. And so finally we can write f in a factored form. So f of x is equal to x minus the first zero, 2 minus 3i, times x minus the second zero, 2 plus 3i. And of course you can write these in any order. And this factorization comes from the linear factorization theorem up above. So lots of powerful information on this page. Be sure to study this thoroughly. Let's look at another example using this information in example 4. Find a cubic polynomial f of x with integer coefficients and zeros of 2 and 1 plus 2i. So first off, the question asks for a cubic polynomial. Cubic means that the degree of the polynomial is equal to 3. That also means that we're going to have 3 zeros. We want it to have integer coefficients. Integers are a subset of the reals. And the two zeros that are listed so far are 2 and 1 plus 2i. Now, knowing that 2 by itself is a 0 doesn't help me with this problem. But knowing that 1 plus 2i is a 0, I can use the conjugate zero theorem. And that tells me that we have another 0 that is its conjugate. So the conjugate zeros theorem tells me that 1 minus 2i is also a 0. And now we have our 3 zeros. So the trick to creating the cubic polynomial is to first write this in the linear factorization order. So this is going to be x minus 2 from the 0 that is x equals 2 times x minus 1 plus 2i times x minus 1 minus 2i. And now we just simply have to multiply this together. Now this looks like a daunting task, but there is a little trick that you can use to help you simplify this. First, let's leave the first factor alone, x minus 2. And then we're going to distribute the negative inside each of these individual parentheses. We're going to get x minus 1 minus 2i, and then x minus 1 plus 2i. And within this result, I'm going to do some grouping. I'm going to group together the x minus 1 here and the x minus 1 here. And I'm going to use the difference of two squares formula. You may recall that if you have a squared minus b squared, this is equal to a minus b times a plus b. Well, I'm going to reverse this. And I'm going to do a minus b times a plus b is equal to a squared minus b squared. And so what that gives me for this problem is x minus 2 times, and now the a is the x minus 1, and the b is simply the 2i part. So using the difference of two squares, this simplifies to x minus 1 squared minus 2i squared. All that inside of big parentheses. Then we can use some of our other tools that we know. We can multiply out x minus 1 squared. That's x squared minus 2x plus 1. and we can multiply out 2i squared. That would be negative 4i squared. Simplifying the right side parentheses, we get x squared minus 2x plus 1. And recall that I squared is equal to negative 1. So negative 4 times I squared is going to be positive 4. Simplify this row, we get x minus 2 times x squared minus 2x plus 5. And then we distribute, and we get x cubed minus 2x squared plus 5x minus 2x squared plus 4x minus 10. Combining like terms, we get x cubed minus 4x squared plus 9x minus 10. And there's our cubic polynomial. Let's look at example 5. Find a polynomial f of x of the lowest degree possible with zeros of negative 1 with multiplicity 3 and 2 with multiplicity 1 that satisfies the condition that f of 0 must be equal to negative 10. So the zeros are going to be x equals negative 1 with multiplicity 3 and x equals 2 with multiplicity 1. Together, the total multiplicity is 4, which means the lowest degree possible is degree 4. So we're looking for a quartic polynomial that has this property. Well, the next thing I can do is write out the linearization, and it would be x plus 1 cubed from the root and the 0 that is x equals negative 1 times x minus 2 with multiplicity 1. We don't really multiply that out, or rather we don't write the exponent there. Now we do need to multiply all of this out, and we'll do this in several parts here. I'm going to split up the cubed into squared and then another one that's to the first power, because I know how to do squares relatively quickly. It's x squared plus 2x plus 1 times x plus 1 times x minus 2. And also I think I'll multiply out the x squared, I'll multiply out the x plus 1 times the x minus 2. That would be x squared minus x minus 2. And from here you can use any technique that you want to multiply these out. I think I'll use my synthetic multiplication technique. 1, 2, 1. And then 1, negative 1, negative 2. And just multiply these out. 1, 2, 1, negative 1, negative 2, negative 1, negative 2, negative 4, negative 2. And then draw the diagonals that separate the terms, and then write out the result. So we have negative 2, negative 5x, negative 3x squared, positive x cubed, and positive x to the fourth. So x to the fourth plus x cubed minus 3x squared minus 5x minus 2. Again, you can use any technique you want. I just find this quick and easy to do. And that is a quartic, and it might be f of x, but it might not be. Because there's one other thing that we have to consider, and that is our polynomials could have been multiplied by some constant, to sort of stretch them away from the x-axis and produce different values. And in fact, one of the conditions that we know must be true is that f of 0 must be equal to -10. This is what we want to happen. What we do have happening here, if we check it here, is 0 to the 4th plus 0 cubed minus 3 times 0 squared minus 5 times 0 minus 2, which is equal to -2. So we don't have it quite yet. So what we're going to do is we're going to rewrite f of x as some number a times the rest of the quartic that we already have. And then we will compute f of 0. It's going to be a times, again, this calculation, 0 to the 4th plus 0 cubed times 3 minus 0 squared minus 5 times 0 minus 2. And that has to be equal to -10. In order for that to be equal to -10, this whole thing here in the center simplifies down to -2. So we actually have -2a is equal to -10, which gives us a is equal to 5. So the coefficient, the lead coefficient, has to be 5, and in fact we can just write and multiply everything by 5. So we're going to have 5x to the 4th. Distributing, we have 5x cubed minus 15x squared minus 25x minus -10. And that's our solution. Next, let's take a look at Descartes' rule of signs. Descartes' rule of signs says the following. If you have a polynomial f of x with real coefficients and a non-zero constant term, then we can find the number of positive zeros from the function f by looking at the number of sign changes of f, or taking that number and subtracting off an even number. And you can find the potential number of negative zeros by looking at the sign changes of f of -x, so note the negative inside the function there, or taking that number and subtracting off an even number. Now this part is the confusing part for most students. It says less an even number. So what that means practically is that suppose we compute the number of sign changes of f and we get 7. Then the total number of positive zeros that f could have, it could be 7, and then we just start subtracting off 2's until we get to a number that can't possibly work anymore. So it could be 7 or 5, or take away another 2, could be 3, or take away another 2, could be 1. If I take away another 2, then it would be -1. And what Descartes' rule is telling me is how many there are. What is the number of possible zeros? So it can't be negative. These numbers are not the zeros themselves. They're just the count on how many different types of zeros there are. And if you have an even number to start with, say you have a 6, then you just start taking away evens here as well, taking away 2's. So 6, then 4, then 2, and you could have zeros of some type, positive or negative. Okay? So what Descartes' rule is telling us is how many zeros of a certain type there are. It's not telling us what the zeros are themselves. Let's see an example. Determine the number of possible positive and possible negative zeros of f of x is equal to 4x to the 5th minus 8x to the 4th minus 7x cubed plus x squared minus 9x plus 13. Do not attempt to find the roots. So what we're going to do is we're going to look at the signs of f, and then that'll help us to determine how many possible positive roots or zeros there are. A sign change is when we go from one sign to another. So let me just write out all of the signs here in the function f of x. Positive, negative, negative, positive, negative, positive. And now what we want to do is we want to look at the sign changes. So we start with whatever sign we have. It's positive and it changes to a negative. That's a change. So that's one. Then we have a negative, no change there. Then we go from negative to positive, that's a second change. Then we go from positive to negative, that's a third change. And then from negative back to positive, that's 4. So there are 4 sign changes in f of x. So that tells me that for the positives, we could have 4 or 2 or 0. So for positives, we could have 4 or 2 or 0. Remember, we just start counting down by 2's until we get 0 or 1. That handles the positives. Now to find the negatives, we need to first compute f of negative x. When we compute f of negative x, we plug in negative x for each of the x's. So it's 4 times negative x to the 5th minus 8 times negative x to the 4th minus 7 times negative x cubed plus negative x squared minus 9 times negative x plus 13. Now we simplify. If we take negative x raised to an odd power, we still end up with the negative. However, if we take negative x to an even power, we lose the negative. And so I'll continue doing that all the way through. This is going to be a negative x cubed plus positive x squared. This one stays the same. And the 13 has nothing there. And now we just sort of simplify everything the best we can. So this has become negative 4x to the 5th minus 8x to the 4th plus 7x cubed plus x squared plus 9x plus 13. Let me write out the signs. We have a negative, negative, positive, 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 positive. Count the sign changes, starting with whatever sign you have. We have a negative, goes to a negative, nothing there. Then we have a negative that goes to a positive. That's one sign change. And then there are no other sign changes. They're all positive throughout. So we have one sign change for the negatives. So negative is one sign change. And that's it for the negative, because we can't subtract 2 and still have a positive or 0 number. So that's it. Now, there is one little chart that you can come up with, and I've coined the term Descartes chart because it rhymes. And so here's what we're going to do. We're going to list all possible combinations of how these roots can actually appear. I'll try to sneak it in right up here. We're a little bit short on space here. Let me put up a dividing line if I can. Yeah, here we go. All right. Now the thing we have to remember is the total number of roots we're going to have is 5. And it's based on the degree. All right, the degree is 5, so we have 5 total. Now we make all combinations between the positives and the negatives. And we only have one choice for negatives. So I'm going to go ahead and put that one choice down. It's 1. But I could have 4 positives. Now, I need 5 total. So if I have 4 positives and 1 negative, that leaves me with 0 imaginary numbers. So this is one possible scenario for the way that the roots could come out of this polynomial. 4 positives, 1 negative, and 0 imaginaries. Now again, let's do another one. So we still have just the one with the one negative number, but I could have 2 positive numbers. Well, if I have 2 positives and 1 negative, that leaves me with 2 possible imaginary numbers. And finally, we could still have the 1 negative. We could have 0 positives, and that would leave me with 4 imaginary roots. And those are all the combinations. I've used every combination between the positives and the negatives. Let's take a look at example 7. Determine the number of possible positive and negative zeros of f of x is equal to 3x to the 6th minus 10x to the 5th plus 2x to the 4th plus x cubed minus 9x squared minus 5x minus 17. So let's look at the signs of the original function. Plus, minus, plus, plus, minus, minus, minus. Count the sign changes. We have 1, 2, 3 sign changes. So for positives, we know it could be 3 or 1. For the negatives, I first need to compute f of negative x. And so this is going to be 3 times negative x to the 6th minus 10 times negative x to the 5th plus 2 times negative x to the 4th plus negative x cubed minus 9 times negative x squared minus 5 times negative x minus 17. And this is going to be equal to 3x to the 6th plus 10x to the 5th plus 2x to the 4th minus x cubed minus 9x squared plus 5x minus 17. Again, count the signs and the sign changes. So let me write out all the signs first. Plus, 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 minus, minus, plus, minus. And we have 1, 2, 3 sign changes. So for negatives, we have 3 and 1 as well. Looking at the degree, we have 6. So there are 6 total roots or zeros that we need to find. Let's create the Descartes chart. And we'll take every combination of the positives and negatives that we have. So we could have 3 positives and 3 negatives. That's a total of 6, so that would leave 0 imaginaries. We could have 3 positives and 1 negative, and that would leave me with 2 imaginaries. Or we could have 1 positive, 3 negatives. That's 4. We need 6 total, so that's 2 imaginaries. Or we could have 1 positive, 1 negative, and 4 imaginaries. And that's the entire Descartes chart. We've made every combination between the positives and negatives. All right, let's put all of this information together to form a coherent strategy for finding the zeros of a polynomial. Step 1, find the possible rational zeros using the rational zero theorem. Step 2, find the number of possible positive and possible negative zeros using Descartes' rule of signs. Use Descartes' rule of signs to eliminate choices, and then check possible rational zeros using synthetic division. Then reevaluate possible rational zeros. The list cannot grow from step to step, but as you find zeros, the list can actually shorten. Continue until you find all the zeros. Remember, the number of zeros with their multiplicities is equal to the degree. And then keep in mind that the zeros of a quadratic function can be found using the quadratic formula. Let's use the strategy in example 8. Find the zeros of f of x is equal to x cubed minus 8x squared plus 21x minus 18, and then write f in the factored form. So first off, we want the possible rational zeros. Since we have 18 here and a 1 here, factoring 18 gives me everything that I need, because all we would do is then divide everything by 1 to get the same numbers. So it would be plus or minus 1, 2, 3, 6, 9, and 18. So that's my PRZ. Next, the Descartes rule of signs. And let me write out the signs of f of x. That would be positive, negative, positive, negative. Counting the sign changes, we have 1, 2, 3 sign changes. So for positives, we have 3, and then take away 2, we have 1. Next, I need to compute f of negative x. One trick that you may have picked up on is that in the new polynomial f of negative x, only the exponents that are odd are the terms that change signs. If the exponent is even, it keeps the sign. So here we have x cubed, that's going to change signs to negative x cubed. 8x squared is going to stay negative because it's an even power. 21x changes signs. And the 18 is technically an even power. It's x to the 0 power. And so it's going to stay negative. Looking at the signs here, we have negative, 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 negative. That is 0 sign changes. So we have no sign changes for the negatives, which means for the negatives, there are 0 roots. So if you look back at our chart, it said step 3 was use Descartes' rule of sign to eliminate choices. So even though we can form these possible rational zeros with the plus or minus, we now know that there are 0 negative roots. These are negatives. And because of that, we no longer need the negative on the PRZ. In other words, now that we're going to start testing by synthetic division, we don't need to test the negatives because we know there are none. There are no negatives that are going to work here. That's the power of Descartes' rule of signs. It allows you to eliminate some choices without even checking them. So let's check the first one here. Let's try 1 inside the polynomial. 1, negative 8, 21, negative 18. Do the synthetic division. We're hoping to get a 0 as the remainder. So 1 times 1 is 1, negative 7, 14, 14, and negative 4. Since we did not get a 0 for the remainder, 1 is not a root. Let's try 2. 1, negative 8, 21, negative 18. Bring down the 1. 1 times 2 is 2. 2 minus 8 is negative 6. Negative 6 times 2 is negative 12. 21 minus 12 is 9. 9 times 2 is 18. 18 minus 18 is 0. Check. We have found a root. So this one is going to work. Now, the best part of this is the following. Because we started out with a cubic, we found a root, and that leaves x squared minus 6x plus 9 as the quotient. So now all we have to do is find the roots or the zeros of this quadratic, x squared minus 6x plus 9. But it is quadratic, so we can do a multitude of things. We can factor it, or we can use the quadratic formula, or we could complete the square. Luckily, I see that this one factors as x minus 3 times x minus 3. And that's going to give me x equals 3, and there's 2 of them here, so we're just going to write that x equals 3 with multiplicity of 2. So now we have the zeros. The zeros are x equals 3 with multiplicity 2, x equals 2, multiplicity 1, we don't write that, and we now have the factored version of f. f of x is equal to x minus 3 squared times x minus 2. Both of these coming from the zeros above. Let's look at example 9. Find the zeros of f of x is equal to 2x to the 4th plus 5x cubed minus 3x squared minus 35x minus 50. So let's start with the PRZ. we need the constant term, 50, and its factors. 1, 2, 5, 10, 25, and 50. And the lead coefficients factors, 1 and 2. And now what we do is we just create every possible division between the factors of 50 and the factors of 2. And so that would be plus or minus. And the first one we'll just divide everything by the 1. So that's just every number in the 50 list here. So 1, 2, 5, 10, 25, and 50. Next we come through and we divide everything by 2. Now if we've already have a number that's in the list, we don't repeat it. So 1 divided by 2 is a half, that's a new one. But 2 divided by 2 is 1, and that's already in the list here at the beginning. So we don't add that one. And then we have 5 over 2. 10 over 2 is 5, not repeated. 25 over 2 is 25 halves. And then 50 over 2 is 25, that's already in the list. So there are our possible rational zeros. Next, let's use the Descartes rule of signs. And I'll just go ahead and list all of the signs for f of x. It's positive, positive, negative, negative, negative. Let's count the sign changes, and I only see one. So that means the number of possible positive zeros is only 1. Next, let me write out f of negative x. Now remember, this is just going to change the sign of the odd-powered terms. So the first one's even-powered, that stays the same. The second one is odd-powered, so it changes from positive to negative. The third one here is even, so that stays the same. The fourth one was odd, it was negative, it becomes positive. And of course the 50 is a constant, it stays the same. Let's count the number of sign changes. We have 1, 2, and 3. 3 sign changes. So for negatives, it can be 3 or 1. Let me go ahead and create the Descartes chart on this one. So we could have 1 positive, 3 negatives. The degree of this polynomial is 4, so I need 4 total, and that's everything. So there would be 0 imaginaries there. Or we would have 1 positive, 1 negative, and 2 imaginaries. And this is all we can have in this case. Now where the Descartes chart is really going to be helpful here is to note that there is exactly 1 positive 0. So we can start looking for it, and further, once we find it, then we no longer have to check for any more positive numbers from the PRZ, because there is only 1 positive. Once we find it, that's it. So that's going to be a helpful tool in searching for the zeros. Alright, so now we're ready to start looking for the zeros, and I'm going to take a shot here with 5 halves. And the polynomial's coefficients are 2, 5, negative 3, negative 35, and 50. And let's go ahead and do the multiplication here. Bring down the 2. 5 halves times 2 is 5. 5 and 5 is 10. 5 halves times 10 is 25. 25 minus 3 is 22. 22 times 5 halves is 55. 55 minus 35 is 20. And then 5 halves times 20 is 50. And, oops, this 50 was negative. And so that's a 0. Yeah, I knew that one was going to work, so that's why I chose it. All right. So that one does work. So 5 halves is a 0, and it is the only positive 0. So we no longer have to look for any positive numbers. We now restrict ourselves to looking for only the negative ones. Next, let's bring down this quotient. And let's start looking for some negatives. Now we have to continue with the synthetic division process because we are still left with a cubic. We need to get that down to a quadratic. Let me just take a guess here and try -2. So bring down the 2. 2 times -2 is -4. 10 minus 4 is 6. 6 times -2 is -12. 22 minus 12 is 10. And 10 times -2 is -20. And 20 minus 20 is 0. So -2 works as well. That leaves us with the quadratic. That is 2x squared plus 6x plus 10 equals 0. We need to solve this. The first thing that we can do is factor out a 2. And that leaves me with x squared plus 3x plus 5 equals 0. And so now we're just dealing with solving this quadratic. It does not factor, so we need to use the quadratic formula. That would be -3 plus or minus the square root of 3 squared minus 4 times 1 times 5 divided by 2 times 1. It's just 2. And sort of bring that up here and work that out. We still get x is equal to -3 plus or minus the square root of 9 minus 20 divided by 2. That gives me -3 plus or minus the square root of -11 over 2. And recall that if we have a negative under the square root, we can bring that out as an I. So we get -3 plus or minus I times the square root of 11 over 2. That's as far as we can simplify that. So the zeros are x equals -2, x equals 5/2, x equals -3 plus I square root 11 over 2, and x equals -3 minus I square root 11 over 2. Notice if I try to categorize these based on the Descartes chart, the -2 one is negative, the 5/2 one is positive, and these two at the bottom are imaginaries. With that information, we can return to the Descartes chart. Let me scroll up here. And you see that the actual one that was used here is this bottom one. So anytime you create the Descartes chart, you should be able to go back and check the chart to see if the configuration of your zeros actually matches one of the configurations predicted by Descartes' chart. If it doesn't, that means there's an error somewhere. The final step in this problem is to write f as in factored form. So we will do that as follows. Now, this one is a little more tricky. We're going to have from the first root x plus 2, then x minus 5/2, and then what do we do with these parts? Well, there's two things that we can do. Number one, we can leave them as the imaginaries. Like so. Put a little parentheses around there. And then put a little parentheses around this other one here. -3 minus I root 11 over 2. That's the linearization form. However, there is a slight problem in that if you actually multiply out what we have listed here, you do not get the original polynomial. That's because the lead coefficient was 2. So, what we do in this case is we just go ahead and multiply it by 2, knowing that Number one, multiplying it by 2 does not change any of its roots, and that there was a factor that was a fraction, there was a 0 that was a fraction, and that 2 will sort of work with it to make sure that the rest of the numbers, when you multiply it out, become integers. So that's the linearization.